live streaming now. We had a little bit of technical difficulty with YouTube getting going. So today's class is still going to end at 11:45. So whatever we were planning to do, I'll just put in tomorrow's class, which is fine because tomorrow we have circular motion again. So it's no big deal, but let's get started. Okay, my name is Angela Jensvold. Welcome. And we're going to review circular motion today. Here's your warm up. And I originally was going to give you 30 seconds for this, but I'm only going to give you 15 now. Okay, that's 15 seconds. I hope you were able to do that. It should be pretty easy. It's just asking you, what is the direction of velocity? So this is an object moving in circular motion, and you need to know that the velocity is tangent to the circle. So in the answer to the question was east. I hope you were able to get that even in the shortened time period. Okay, so today we're going to look at 3 learning objectives, interactions 2A, B, and C. Calculate the velocity of an object moving in uniform circular motion. Calculate the relationships among position, velocity, and acceleration for uniform circular motion. Explain how the sum of forces in the radial direction can be one force, more than one force, or components of forces. Describe forces on objects in circular motion. Describe forces that are acting on different objects traveling in different circular paths. Describe the direction of hey, didn't we just do this? Describe the direction of velocity. We did. Okay, so part of our mission is accomplished. We're going to also describe the acceleration for circular motion, calculate the resultant acceleration for non-uniform circular motion. Okay, so here are the main ideas for circular motion. When an object is traveling in a circle, there's a component of its acceleration that points toward the center, and the magnitude of it is the speed squared divided by the radius. Uniform circular motion, in that last side, I kept typing UCM. UCM is uniform circular motion. That means you're going in a circle at constant speed. So in any circular motion problem, you need to analyze the motion by drawing a force diagram, sum the forces in the radial direction, and apply Newton's second law. So along the forces along the radius. If an object's speed is changing, then that's not uniform circular motion. You'll need to find the components of the acceleration and then add the vectors. Okay, so now let's see if you guys can figure out the direction of the acceleration for this one. I'll give you 30 seconds. Okay, I hope that was enough time. I cut it in half because I think it was fairly easy. The direction of the acceleration, we said that when an object is moving in a circle, there is a component of the acceleration that points along the radius, the radial acceleration, toward the center of the circle. And this object, it says it's slowing down. Now, in the last slide, didn't we say that the velocity, it's the same situation, the velocity was pointing east, right? So if the velocity is pointing east, but it's slowing down, it must have a tangential acceleration that is pointing west. So this is the tangential acceleration, right? So it has 2 components of acceleration. So to get the overall direction of acceleration, in order to describe the acceleration, I would say south of west or west of south. Either of those would be good. So I hope you had enough time to do that. Okay, this one, I'll give you all the time. Okay, so I'll let you read it and I'll give you a minute to give it a shot. Okay, so let's just draw a little picture first. Okay, so we have car A, and it's going around a circle at constant speed. And we know that maximum speed, the acceleration points toward the center, right? So if it's going constant speed, that means there's no tangential acceleration. There's just this radial acceleration that points toward the center. I just like to visualize what's going on by drawing a sketch first. Okay, so what is it saying? Car B has twice the centripetal acceleration as car A. Okay, well, the acceleration that points toward the center is v squared over r, right? This would be the velocity of B. Why didn't I put subscripts on the r's? Because it's the same circle, so the r is the same. So I'm going to cancel that, and I get velocity of B is the square root of 2 times the velocity of A, and velocity of A is 10 meters per second. So you should get 14.1 meters per second. Okay, there's a lot going on here, so let me just explain. The diagram on the left is a bird's eye view. So you have these two blocks that are being pushed around in a circle, and there's a vertical wall that's preventing the blocks from moving in a straight line due to this applied force. The side view, you can see that applied force from the left, and there's that vertical wall. Now the horizontal surface doesn't have any friction, but the vertical surface does. So, and there it says it's traveling at constant speed. Okay, so you're trying to find the value of the applied force. Give it a shot. Okay, so why don't we start off by using the fact that it takes 10 seconds to go all the way around. I think we can get the speed that way. So speed is distance over time, right? And if you're going in a circle, the distance would be their circumference, 2 pi r over the period. So it'd be 2 pi times the radius, 1.25 meters, divided by the period of 10 seconds. So you should get 0.785 meters per second. Okay, so that's the speed that it's going around in the circle. And we're trying to find the magnitude of F. So let's see. Why don't we draw a force diagram from the bird's eye view? What is causing this object or these objects, the system of objects, from going in a straight line at constant speed? There is a force that's changing its direction, and that's the normal force from the wall on the blocks. Okay, so I'm glad I used these subscripts because you might be tempted to use mg for the normal, but this is not, normal is not always equal to mg. So I recommend that you always draw a force diagram to figure out what your normal is, because you could get into trouble if the object's on an inclined plane, for example, normal's not mg. And in this case, again, we have an instance where normal is not mg. So really you have to draw your force diagrams. Okay, so we've got normal there. And if we look at Newton's second law, if we apply Newton's second law in the radial direction, this is what it looks like, right? Radial acceleration equals sum of forces over mass. Well, radial acceleration is v squared over r, right? What are all the forces acting in the radial direction? Is capital F a radial force? No. Normal is normal of the wall on the blocks. I'm leaving the subscripts in because I really don't want to be tempted later on to use normal equals mg mindlessly. Okay, we really have to think about the meanings of these physical quantities. Okay, so we're trying to find F, right? So what do we know here? Let's look at the side view. We've got the applied force is to the right. We know friction from the ground on the blocks would be pointing to the left. And if you look in the horizontal direction and you apply Newton's second law, you know that the acceleration in the horizontal direction is 0. So that the sum of forces in the horizontal direction would be that applied force minus friction of the ground on the blocks divided by the mass. So what does that tell us? That tells us that the applied force is equal to the friction of the ground on the block, right? Okay, so what do we know about the friction of the ground on the block? Okay, it's mu normal, right? It's mu times normal. What normal? The normal of the wall on the block? What normal should we use here? You know what I think we need? I think we need a force diagram. We better draw it from this side view, okay? We've got the force of the earth on the blocks, and we have another normal force. How will we distinguish it from the other normal force? We're going to use the subscripts. We want to emphasize that every force is an interaction between two objects. What two objects are interacting here? The ground on the blocks, okay? So if you analyze the Newton's second law in the vertical direction, so we've got horizontal direction, vertical direction, radial direction. Wow. Okay. Then you have normal of ground on block minus force of the earth on the block over mass. And the acceleration in the y direction is 0. So what that means is the normal of the ground on the block is equal to mg. This time normal is mg. But remember, a moment ago it wasn't. So that's why we have to go through this whole process. Okay, so my rant is over. Mu mg. Okay, so we've got the friction, the force is equal to friction. Oh, shoot, I did this all wrong. So what is causing friction? Is it the friction from the ground? No, it's the friction from the wall, right? So we should be using so friction is mu times normal, but the surface that's causing friction is the vertical one, wall, on, blocks. Wow. I was trying to do friction from the horizontal surface, but they told us in the problem that there's no friction in the horizontal direction. It's very important to read all the words. Now we got to go back over here and get the normal from the wall on the ball is equal to mv squared over r. Now we can come back over here and plug it in. Mu mv squared over r. I don't know, my screen just froze. I don't know how to fix that. I guess you guys can see over here. You can tell something happened because it looks weird, right? I'll just try to do it from my laptop. V squared. Oh, I have no. A lot of technical difficulties today, huh? That's online teaching for you. I want to draw. Let me see if I can do it. This was supposed to be squared. I'm drawing with my finger, so please forgive me. And then when you plug all that in, you get the force of 0.345 newtons, 0.3. I'm trying to draw with my fingers, guys. Newtons. That's friction force. But guess what? Look right below that number. The applied force is equal to friction. So the answer is 0.345 newtons. Okay, let me see if I can get my screen back, my iPad. Nope. Oh boy, I don't know how to fix that. Oh, okay, there we go. All right, so why don't you guys try this one? I'm going to give you 1 minute to do it. Okay, so let's draw a picture so we can visualize what's going on. So you have an object on a string, and it's moving in a horizontal circle of radius r, and the tension in the string is force of string on object. If you double the frequency and the radius, what happens to tension? Okay, so let's analyze this situation using Newton's second law. So we're summing the forces in the radial direction. So in the radial direction, you've got V squared over R equals, it's just tension, right? Force of string on object. Okay, so if you solve for the force of the string on the object, you get mv squared over r. But we need to have frequency in here somewhere, right? So let's write out, what was v on the last problem? 2 pi r over the period, right? Well, they didn't give us the period. They gave us the frequency. Do you guys remember that frequency is 1 over period? So then it should be 2 pi, rf. If I plug that expression for velocity in, I will get the force of the string on the object equals m. Now I got to square this v. 4 pi squared r squared f squared all over r. So it's 4 pi squared m r f squared. Okay, now we got to think about what would happen to this tension if I doubled r, so times 2, and I doubled the frequency. I want to take the frequency and multiply it by 2. Well, the frequency squared, if you double it squared, that'd be 4 times as much. Multiply it by a doubled radius, you would get 8 times as much. So the answer is 8 times the original force of the string on the object. Okay. Okay, this is a nice one. Read this and give it a try. Okay. I really like this question. It's an old AP question. It's a dancer on a music box. The path lengths are equal. So the length of PQ and QR are the same. QR and SP are semicircles. Describe the acceleration. You know what we should do? We should type this. Let's practice for the exam. You're going to be able to type your exam if you want. So why don't we do it? Okay. The acceleration for P, Q, and RS are 0 since the speed is constant and the dancer is not changing direction. The acceleration for QR and SP is constant and non-zero. 0. Constant and non-zero because the speed is constant and acceleration is v squared over r. Okay? Yep. We don't need superscripts. We can use little caret, and then we've got a v squared. Okay? All right, I hope you guys like that one as much as I did. Okay. Just need to find my cursor. There we go. Okay. Okay, give this one a try. Give you 1 minute. Okay, first, let's go with this first statement. You can hang 10 kilograms before this string breaks. So let's draw a picture of that. So 10 kilograms. This is right at the edge between where the string is okay and where it breaks. So what do you have here? You've got the force of the earth on the block, and you have the tension in the string on the block. And if this thing is in equilibrium, hasn't broken yet, then those two forces should be equal, right? So basically what that tells us is the maximum tension is 100 newtons because the force that the earth pulls down with is equal to mg. Okay, so now we know the maximum tension is 100 newtons. I just want to draw a picture of the circular part of this. You're going to take an object, swing it around in a circle, and connect the string to it. And you want to know how fast can you spin it before the string breaks. So let's use Newton's second law in the radial direction. So in the radial direction, you know acceleration's v squared over r. And the sum of forces in this particular case, when we look at our force diagram, the only radial force we have is tension. And we specifically want the maximum tension. And if we solve for the speed, that would correspond to the maximum speed, right? Maximum tension corresponds to maximum speed. So solve for maximum tension, maximum speed, and you get radius times max tension over mass. So the radius is 2 meters. Maximum tension is 100 newtons divided by the mass is half a kilogram. Let's see if we can do this without a calculator on our heads. Okay, 2 times 100 is 200. 1 over half, you flip it up, so you would get 400, right? Can you do square root of 400 in your head? I think it's 20 meters per second. Okay, so we didn't even need a calculator for that. What's the minimum coefficient of static friction to keep this car moving? Okay, so what is given? They gave you mass, speed, and radius. So let's just draw a bigger diagram. Here's your car. What force is causing this object to change its direction? That's friction. Friction of the ground on the car, right? Okay, so what we want to do is find the minimum coefficient of static. Should we try typing this one out just to practice for the exam? We can. Let's see if we can do this. Okay, so we're going to do the same thing we've been doing. We're just going to type it. So we're going to start with Newton's second law, right? A equals, just do sum of forces. How about that? Sum of forces. Can't you put a parentheses around that? Forces divided by mass. Okay, so should we specify that that's radial? So we could do a capital A and an R. Radial acceleration. Okay, maybe. We also know radial acceleration is v squared over r, right? So if we plug that in, we'll get v squared over r is equal to sum of forces, which is just friction, right? F over m. Okay, so the friction is mu normal, right? So v squared over r equals mu normal over m. Okay, we're trying to find the coefficient of static friction. So we're going to need normal, right? So we got to draw a force diagram after my rant earlier, and especially my error, normal of ground on car. There's no other normal here, right? It's not like that other crazy problem. It's just a horizontal surface. There's no vertical wall. And then you've got the force of the earth on the car. Okay, now here, there's no acceleration in the vertical direction. So that means the normal force would equal mg this time. But we do that every time just to make sure. We don't want to mess this up. So we have v squared over r equals mu times normal, which is mg over m. Well, that m is going to cancel, isn't it? So I'm going to say v squared. I'm going to move the r to the other side, okay? So r times mu g. So v is, I'm going to put a bracket, r mu g to the square root. Okay, that's the answer. Oh, did I forget an equal sign? V equals. We did it. It can be done. Okay, so if it were me, I would type it, because I'm, as you've seen earlier, I'm not as great with technology, so uploading makes me nervous. But you guys do what you want to do. I'm just showing you it's possible. It's possible to type it. Okay, I always lose my cursor. Took forever. Okay, so right now, this object has a mass m, radius r, and a constant speed v, okay? And under those conditions, the force, the sum of forces on the object is F. Then they stopped it, started from rest, and they spin it so that it's speeding up with an acceleration A. What's the new force? Okay, so now the new scenario is that it's going to be speeding up. So that means that it's going to have an acceleration in the same direction as the velocity, right? When it's speeding up. So that means that it's going to have a tangential force acting on it. And the magnitude of that force will be equal to ma. So you have the inward force toward the center, that's magnitude F if you assume it's going at the same speed. And then you have ma. So to get the new overall sum of forces, you would have to do Pythagorean theorem. So the new force, what are we going to call this? F prime, I don't call it whatever you want. F prime is the square root of F squared plus ma squared. Okay? Okay, there's a car going in a horizontal circle with a mass m, speed v, radius r, and when it's on a banked curve, it can go faster without slipping. Why is that? Okay, what do we need to do to figure out the answer to this question? We need a force diagram. In the first one, the only thing pulling you toward the center is the friction between the ground and the car, right? But in the second one, you've got friction from the ground on the car, and you've got normal force from the ground on the car. Both of those forces have components that point toward the center of the circle. So normal force has a component that points toward the center of the circle, and friction has a component that points toward the center of the circle. Okay? So the reason you can go faster on a banked curve is because you have normal helping you push toward the center to change your direction. Okay, find the acceleration at the top of the hill. Okay, so find the acceleration at the top of the hill. It's saying it slows down at a constant rate. So if it's slowing down, that's tangential acceleration, right? So if you show this thing, let's say it's moving this way, that means the acceleration is the opposite direction. So it has a tangential acceleration. It's also going over the top of a hill, which means it's changing direction. So it has an acceleration along the radius as well. So let's start off with the tangential acceleration. And this is the tangential acceleration. So it'd be v squared minus v naught squared over 2 delta x. So final is 10 minus 25 over twice the distance. So 10 squared is 100, right? 100 minus, I think I calculated this somewhere. I don't know where I put it, but anyway, it's 100. Let me just see, 100 minus 625 over 100, negative 5.25. Does that sound right? I think it's negative 5.25 meters per second squared. I think you could do that without a calculator, but it's pushing it. Okay, so that's the tangential acceleration. And then the radial acceleration, we know is v squared over r. So at the top of the hill, the speed is 10 meters per second. Okay, we gotta cut it short today. Divided by the radius, which is 25 meters. 100 over 25, we can do that in our head. That's 4 squared. Okay, so to get the overall, the total acceleration, you would do square root of 4 meters per second squared plus 5.25 meters per second squared. And if you square root that, you should get 6.6 meters per second squared. Okay, we had a little problem at the beginning today with YouTube, so our class was cut short. So it's fine because tomorrow we're doing circular motion again. So we'll just continue with this tomorrow, okay? I'm gonna leave you with a question. I'm gonna leave you with this one, okay? I hope I'll just read it to you to make sure you can read the small part. A particle of mass m moves counterclockwise around a horizontal circle of radius r. The angular speed of the particle is given by omega t equals bt, where b is a positive constant and t is greater than or equal to 0. Okay, all I want is the direction of the particle, the direction of the acceleration of the particle, okay? So that'll be a nice warm up for tomorrow. Make sure you get that answer before tomorrow. I'm not asking for much, am I? Okay, so everybody, thank you for watching, and I will see you guys tomorrow. Everybody stay home and stay healthy.